talk about chapter 6, we start out by talking about vectors. Vectors, you know what a vector is? Like an arrow. If you ever sit next to a physics type and they're doodling, giving ideas, talking about things, usually they put a whole lot of arrows to represent things. An arrow is a vector which represents like which way and how much. You know, like when we talk about flying into the wind. Notice in the textbook we talk about the airplane flying into the wind, and we can let the speed of the airplane, maybe the airplane's going due north, something like this, okay? We could let that arrow be the speed. Maybe it's 100 kilometers per hour, so I'd make it 100 units long. And let's suppose I'm going into a headwind, and the wind's coming toward me at 20. Well, I can go like this, say, make an arrow 20. And when I combine these things, my ground speed's going to be what? This, take away this, so it's going to be that much shorter. Sort of like that, you know. And if you're going again, and this time the wind's coming behind you, a tailwind, and you're going again 100 with respect to the still area, and then if you got, say, a 20 coming behind you, those two things combine to be what? You're going faster. Do you need vectors to explain this idea? That if the wind's behind you, you go faster. If the wind's in front of you, you go slower. Answer begins with an N. No, you don't be needing vectors. But I'll tell you where the vectors do come in handy. Like you got a crosswind, okay? Let's suppose you're flying like this. And let's suppose the wind is a crosswind coming like this, just as fast as you're going. Let's suppose you're going 100 kilometers per hour, and you're in a hurricane, and the hurricane's coming like this at 100 kilometers per hour. What's the direction of the aircraft going to be? It's kind of easy to see, isn't it? Huh? It's kind of going like this, it's kind of going like this at the same time, right? And so what it does is it kind of goes off course like this, huh? Let me give you a neat little rule. We'll tell you exactly which way and how fast it goes. And the little rule is this. Take your two vectors, one representing ground speed, or the speed through the air, huh? And the other representing the speed of the wind, and make those into a parallelogram. Since they're at right angles here, that parallelogram is going to be, in this case, a square, because the sides are equal. Make a square. And then what you do is you join from here to the diagonal, and you make a vector like that. And guess what, gang? Guess what? That's the direction that the aircraft will travel. And furthermore, it tells you how fast it's going to travel. Because if this is 100, and this is 100, and that's a 45-degree angle, and it would be for both 100, yeah? It turns out, so this will be the square root of 2 times 100. Something like 140. So you'd be going something like 140 kilometers per hour that way. Isn't that kind of neat? Let's suppose instead the wind weren't so strong. Let's suppose you're traveling like this, and you got a crosswind about like that. Now, at your seats there, you guys taking notes, yeah? At your seats, draw this, and what I'm going to do in a minute, I'm going to go ahead and draw the solution, and you guys are going to look. But why don't you beat me to it? Why don't you draw what I'm going to do next to show sort of this thing here, but the angle is different, yeah? Why don't you do it before I do it? Go. Which is to say, you'll make a little rectangle, yeah? See how now this is a rectangle? And what's the diagonal of that rectangle represent, gang?
The direction.
That's right. Now you'll be blown off course only that much. And you know what? If you had a ruler and you did this to scale, you could measure that compared to this, and you could tell how fast you're going to go. Because the velocities will add together in that vector way. Really kind of neat. Any questions about that? So when we talk about how fast things go and we talk about velocity, we're really talking about direction too, yeah? And so we can represent that direction with an arrow. You know, I take this bowling ball and I roll it across the table. Okay. As it rolls across, let's suppose I took strobe pictures. One here, one here, one here, one here. Equally spaced times. You know what? I'd find equal spaced times would give equal spaces of distance. Do you know why? Because the ball's rolling at constant velocity. I mean, it's rolling here, then here, then here, then here. So my little velocity vector would simply be like this. I'm trying to draw that so all these are the same. Why? It's got the same speed along. See? It goes at uniform velocity, see? It takes a little push to get it going, but once I get it going, I let go. It kind of rolls of itself. And it rolls steady, 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 okay? And so these little vectors would just show me that it's rolling at constant velocity. Let's suppose instead I take it and I drop it. What's going to be now? Here it is up here, say. Then I drop it, it goes to here, then to here, then to here, and maybe down in here. Now up here, no velocity, but over here, a little bit, and over here, a little bit more. And you know the velocity is increasing because it's accelerating. Remember we talked about acceleration? And when the acceleration is due to gravity, we just called it g. Remember that? And we know that g for the planet Earth is, check your neighbor. What's the numerical value of g for the planet Earth? Check your neighbor. Don't say 9.8, let's round it off. What's it going to be? Begin with a T. 10, okay? Right? It's going to be 10 meters per second every second, right? That'd be acceleration due to gravity. And because it's accelerating, it's going to keep going faster and faster, true? That's why I make the arrow a little bigger here. It's faster here than here. And over here, I make it like this, even more. And that's because the speed picks up according to the acceleration and time. And the longer the time, the faster you're going. But you know that anyway. And so this is the relationship we talked about last time. How fast something goes depends upon how much it's accelerating and how long a time it's doing that. Isn't that true? Let's do a review. If I took this thing and held it up in the air and let it go, at the end of 1 second, what would its speed be? 10 meters per second, see? Because it started at 0. It's going to pick up to 10, okay? Let's suppose another second goes by. How fast is it going to be going? 20. Let's suppose 10 seconds go by. It's 100, see? Because every second goes by, it's going to be going 10 meters per second faster than the second before. To be sure you understand that, let's talk about this. Let's suppose you're downtown, you're looking out the window, and all of a sudden, whoom, this thing falls right by the window. According to my calculations, that bowling ball just fell by the window at 50 meters per second. Someone says, how do you know that? Oh, I just know that. 1 second later, boom, hits the ground. Sounds okay, how fast was it going when it hit? You couldn't see it then. Check and see if you're sitting next to somebody know the answer to a question like that. How many say 60 meters per second? Show of hands. My people, all right, that's right. Because every second go by is going to pick up 10 meters per second more than it had before. We're learning this stuff, huh? Let's suppose I said 1 second after that, what would it be? 7. See, it keeps picking up the same. Well, here it is right here. G is going to be 10. Let's just call it 10. If G is 10, just multiply by the number of seconds. Even if I told you it falls in 7 seconds, you can still do it. Maybe not 9 seconds. Okay, 9s are kind of tough, but say 7s, all right? 7s, you just say 7 times 10 is 70. How about I give a decimal? 7.9 seconds. Ooh. Remember the first time you saw 7.9? Oh, God. What's 7.9 seconds, gang? How fast it going? 79, whatever it is, okay? It's 7.9 to multiply by 10. Isn't that neat, huh? So that's the review, okay? Now, here's the more important question. Lee, question.
Yeah, so let's see. Last time we were talking about throwing a ball up in the air and then having it drop.
Yeah.
And so at the top, its velocity was 0. Or when you originally let it go, its velocity is 0.
That's right. Starts off at 0.
It started going down.
That's right.
People seem to have trouble with that.
That's right. Here it's 0 right here, Lee, okay? I drop it, now it picks up. Picks up, picks up, picks up, da, 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 da. And all we're saying is there's a relationship for how much it does pick up. It's simply G. And knowing how much it picks up then tells you how fast it's going. And that's just G multiplied by T. Is this too abstract, gang, when I say G and T and things like that and I'll get alphabet? You know, some people like numbers, okay, but this is numbers, this is alphabet. Remember when you first get into that, you get into algebra, and you looked in the algebra book and there are no more numbers, all alphabet? You know, alphabet equations? Well, that's what this is. Does this turn anyone off? You can kind of see what we're talking about, can't you? When you take music, honey, you got to learn how to read the music first, yeah? Isn't that right there? Okay. Well, what we're doing is we're learning how to read the music of physics. The relationships, and we're just putting them in a musical way. Okay? How many people are tone deaf? Okay. I am a little bit. But anyway, that's what we're going to do here. Does that answer your question, Lee? So that's the speed we're going to pick up. Now I'm going to get to the part that's a little difficult for some people. That's how fast it goes. How far is it going to fall? Oh, some people get all mixed up. How fast, how far? How far is different than how fast, right? And how about it, gang? When I drop this thing, you're going to pick up distance, yes? You see it getting further and further apart, huh? What is the rule for how far it falls? Is there a rule? How many say, no, there's probably no rule for that. It's different every time. Come on, gang. What's the rule? You remember? Yeah. It was distance falling, d for distance, equals average out the g, t squared. And if g is going to be 10, and it will be for the planet Earth, then a half of 10 is 5. So we could just say 5t squared. So we should be able to find from here that that distance keeps getting greater and greater and greater the greater the time. That being true, you can answer this question. I take this bowling ball, I get up on top of a cliff, and I drop it. How far down is it underneath? 1 second later. Check the neighbor. How many say begins with an F, ends with an I? Yeah, it's 5 meters. 5 meters down. Okay? Remember that. Any object that falls from rest will fall a vertical distance of 5 meters in the first second of fall. If 2 seconds goes by, how far will it have fallen then? Even more. How much total? And how would you find it for 2 seconds, gang? You got your little rule right here. If 2 seconds goes by, you take 2 times 2 is 4 times 5, 20 meters. It will have fallen 20 meters. And let's suppose 10 seconds went by. You're in an airplane. You drop it from an airplane, it takes 10 seconds to hit the ground. See if you're sitting next to someone knows how fast, not how fast, how far down the ground is. Well, 10 plus 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 10 or what? It's 100, honey. 100, okay? So now you got 100 times, it's going to be 500 meters down. So if you're ever falling off a cliff and it takes 10 seconds to hit the ground, your last thought will be, hey, I fell 500 meters. That's how far you'd go. Kind of see that? Any questions on all this? So we're really summarizing what we talked about last time. There's a difference between how much you pick up speed, okay, and this between how fast you're going and how far you're going. And for falling things, the acceleration will always be the same, 10 meters per second. Later on, we'll round that off to 9.8 meters per second, okay? But 10s are easy to deal with, right? And we find out that how fast we go is simply the acceleration multiplied by how long you've fallen. Makes sense. And then how far you go has to do with the time squared. So it's averaging out 5t squared. How we got that is derived in the footnote of your book, and you can kind of go back and look at that if you want. I don't expect you to derive that. I want you to just know this doesn't pop out of the air in magic, okay? There's a reason for this. Remember we talked about how that came about last time? Look it up if you want. What's kind of interesting is the behavior of the ball when it rolls off the table. I don't think I'll roll it off the ball. I might wake up the people downstairs. But can you, it's going to kind of curve, isn't it, gang? It's going to curve. And you know, that curve wasn't understood for a long time. And when that curve was understood, it was kind of exciting. And let's talk about that. We can kind of show that up here. It's all in your book. Let's suppose I roll the ball. The ball's rolling at constant velocity. I got it going somehow, but once it's rolling, it's rolling. And let's suppose there's no gravity at all, none. You know what's going to happen? The ball is going to just keep rolling like that. And if I have an arrow representing the speed at every time, it might be something like this. And you know why that speed stays the same? It has to do with the idea we call inertia. Once something's moving, it's going to keep on moving unless something messes with it. And so when it rolls off, if there's nothing pushing it this way, then it will just keep going at the same speed. Like when this ball is rolling along, and now I push it. When I push it, it gains speed. But if I don't push it, it'll just keep rolling steady, steady, steady with no change. And furthermore, there's nothing this way obstructing it. Now, there is some air drag, but very, very little compared to the tendency of that ball to just keep crashing through. So the ball goes steady, steady, steady. And rolling off the tabletop, if there's no gravity, would continue steady, steady, steady. But it doesn't continue like that because there is gravity. And gravity pulls it down. What gravity's going to do is like this. The ball, we just hear it dropping. If I let it go, it would fall to here maybe. Then fall to here. Then fall to here. And then maybe fall down to here. Okay? And then I'd have like a little speed like this, a little more like this, and a little more like that, and down here even more. What happens as the ball is traveling like this? It does this. It falls. So when it gets out to here, it really doesn't. It never does get out to there. It falls underneath. Guess how far underneath it falls? One guess. All right, two guesses. It's going to fall right to here. And instead of getting out to here, gravity would have pulled it down to guess how far. It will exactly match what's happening over here. Kind of neato, huh? It will fall to here. And then instead of getting out to here, no table to support it, it will fall underneath. Guess how far underneath? Such as to match right here. And then instead of getting to here, it will have fallen down to, I can't draw that down here, but see, I get the idea? Now look what happens. See this speed here? I'll put that over here. Put this one here. And when I combine them, I get a speed like that. Can you see that? And when it's over here, it still has that speed sideways because nothing's messing with it sideways. That part remains. But now gravity's pulled it down. So it has the same speed it would have over here. So I put this over here. And when I combine them, it's like the airplane flying into the wind, crosswind, huh? What I get is like that. It's picked up speed due to gravity. And over here, it has the same speed here. We call this the horizontal component of the speed. We call this the vertical part, or the vertical component. Component's more fancy than part. Huh? So we have a horizontal component and a vertical component for every one of these speeds. Over here now, my vertical component, longer. So I get something like this. So the path of the ball really is, that's not drawn very well there. Should be a little more. I get the idea. Like that. And hence the ball curves. But the neat thing is that what happens sideways doesn't change. It's only the downward part that changes. And you know why that's true? Because gravity pulls which way, gang? Begin with a D. Ends with an ow. Try it. Down. Gravity pulls down. And so guess which way it accelerates? Down. How about accelerating sideways? No. So the sideways part stays the same. Isn't that nice? Take a cannonball and you throw it up in the air like that, okay? Here's a speed like this. Speed gets less, less, less. Now it starts to pick up. All along here, the sideways part stays the same. The sideways part doesn't change. Only the vertical part does. And that's kind of neat. And human beings didn't know that for a long, long time. The sideways part doesn't change. Question?
One thing that might have interfered with them figuring it out is the question of how long does it have one of those speeds drawn there? How long does it have that speed? Are any of those an average speed?
Yeah, well, no, this would be the speed at any instantly. Now, in the absence of air drag, turns out with a projectile, usually there is a lot of air drag, like with a cannonball. But in the absence of air drag, that horizontal component of speed stays the same. That means it will always be kind of going this way. I'll tell you an interesting application of that. You know, when you throw a rock off a cliff, it keeps going out, 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 and it gets steeper, 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 right? It'll never get so steep that it's vertical, because it'll always have this component of speed. You know? It's like where I live at a place on the 32nd floor of a building, okay? And down here there's a swimming pool. And up on the top on the lanai, sometimes I think about, well, rather than get in the elevator, come all the way down. Have to come out, open the door, go through the gate, come in, why not just... And I often wonder if I could make it. Now here's the thing that's kind of interesting. You kind of look over there and you wonder if you could make it. Well, it turns out I'm so high that it'd take about 4 seconds for an object to fall. Okay? If I just stepped off the balcony, it would take 4 seconds to hit the ground. Let me ask you folks a question. How about if I jump out sideways? How many seconds? Begin with an F and with an O. Try it.
4.
Same 4 seconds. You see what I mean? This ball that rolls off the table takes the same time to hit as one that drops. Do you believe that? Remember the first day we talked about the rifle? You take the rifle and you fire it, and you let go of the bullet. One bullet falls down, the other goes out. Which one hits the ground first? We talked about this. Which one does hit the ground first, gang? Take a guess. I'll give you a hint. SS. Same. You not be knowing that? Let's try it. And I'll come back to this swimming pool thing in a minute. There's a little device here that will shoot a projectile. Little spring here. I'm going to compress the spring. And when I do that, I can put a projectile here and watch this, gang. A little spring gun. Okay. And out it goes. No surprise. But I've got another ball that I can put on the end here like this. And when I go like this, it falls essentially straight down. A little bit out, okay? But kind of downish. When I do them both at the same time, you guys got to figure out, hey, which one going to hit the ground first? The one that just dropped down or the one that goes out? A lot of people think, oh, the one that's fired out is going to be in the air for a longer time. You know why? Because gravity going to start to pull it and say, oh, I didn't know you were moving, go ahead. And gravity not going to pull so hard. What do you guys think? Let's try it. I tell you what. If you hear this, all A's. All A's. For this course, all A's. Registrar say, Hewitt, my guy, Hewitt, you got all A's in your class. I'll say, I had a sharp class, honey. I had a sharp class, all right? All A's. But if you hear this, then you gotta do your homework, okay? Here we go, gang. Here we go. This next moment may be very important for a lot of you who have your, everything riding in your grade. All right, here we go. Here we go. Listen. What'd you hear? How many heard this? Wishful thinking. We'll do it one more time in slow motion. All right? Now you can get a better look this time. Slow motion. Here we go. All right? Same time, gang? Yeah. Gravity doesn't take a holiday on an object just because it's moving. It's going to take the same time to come down. And so we find that over here, too. Drop one ball, throw another ball out, same time.
I was wondering, since you have the, if the thing's just dropping straight down, it goes 10 meters per second, but if it also is going horizontally, doesn't that object have to be traveling at a faster speed than the one that's just dropping vertical?
If you're going to get an angle that's more out this way, yeah. See, what happens in free fall, though, the vertical speed will keep increasing and become very, very big compared to that horizontal speed you have. So it looks like you're going straight down. What do they do in the old cartoons where the roadrunner runs off the cliff? You know, the roadrunners run like this, okay? They go straight down. But it's a little bit different than that, gang, isn't it? The roadrunner really goes like that. Always going this way all the way down, though. A lot of people don't realize that. They think you go like this and then straight. You don't go straight. There's always a little angle. And that angle gets steeper and steeper as time goes by. But here's the point I want to make, gang. If it takes 4 seconds to go from here to here, it takes 4 seconds to go from here to here. So I ask people when I get up there, do you suppose if you jump, you could hit the pool? And how would you find out? And here's what you do. You figure out how far out you could jump in 1 second. Okay, in 1 second. Then multiply that by 4 times. And you got it. It turns out you really hit way down here. I mean, I hit something like way in here. Say, in 1 second I can jump that far. 2 seconds that far. 3 seconds that far. 4 seconds that far. So it turns out it gets very, very steep very, very quickly, and you can't get so far. A knowledge of physics. You people are going to find out that as you learn more and more physics, your social life is going to increase. Because people are going to gather around you. People are going to find you more interesting, okay? Because you're going to have things to talk about now, okay? It's like the time years ago, a fella came to the town in San Francisco and was kind of lonely, didn't know anybody, and wanted to make some friends. So what do? Go to church on a Sunday morning, huh? He went to the church on a Sunday morning. The good reverend says, hey, gang, we're going to meet this afternoon at 2 o'clock. We're going to take a bus trip. We're going to take a bus trip out to hang gliding territory, out on the cliffs over the beach. So all the people get together and they get in this bus and they take us, go way out where the hang gliders are, these big cliffs, okay? And the people get out of the bus, they spread out the big cloth and put the Kentucky Fried Chicken, the Kool-Aid and all the stuff there, the McDonald's and all the other things right there, right? And this guy's sitting down there, he's kind of not checking out the food, checking out the potential friends. Looking around, trying to find out who's who, looks across the way and sees someone and says, this is it. Boom, 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 is it? Okay, finally happened. And he looks at this lovely, lovely person. The lovely person walks over to the edge of the cliff and looks down and says, gee, I wonder how high we are above the water. How high above the water? You guys remember this? How high above the water? He said, wait a minute, I can do that. Some other guy gets up, walks over to the edge and say, how high we are above the water? Here, watch this. Watch this rock. 5 seconds. 5 times 5 is 25. 25 times 5, 120. We're 125 meters high. Delightful person looks at that and says, wow, okay. And they're getting together fine. You're sitting over here, and what are you doing? I could have done that. You miss out. You miss out. You gotta be fast. You gotta be fast. Lonesome city, honey. Lonesome city. You strike out. They're getting along fine. At least you can feel happy for them, right? Next week comes. You go to another church. The reverend type says, all right, all you lonesome hearts out there, we're going to get together today. 1 o'clock today, we're going to get a bus trip together. We're going to go picnicking. So all you new folks, come on. We all get to celebrate life. We get to meet each other. Come on, 1 o'clock, come on, huh? 1 o'clock come, you get in a bus, different color bus. This time it's a green bus, okay? You get on the bus, you go out to the hang gliding territory. Watch the hang glider soar, huh? A little further upstream, okay? You're sitting down. They put out the big tablecloth, the Kentucky Fried Chicken, the Kool-Aid, the McDonald's, the Burger Kings, whatever, all of you know right out there, right? You ain't checking out the food. What are you checking out? Potential friend again. And son of a gun, if an even more delightful person, okay, bam, 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 gets up, walks over to the edge and says, I wonder how high we are above the water. You're back here and you say, Santa Claus has come to town. You get up, you walk over, you grab a rock, you say, watch this, I'll tell you how high we are. You take the rock and you drop it, all right? You drop the rock, but you're a little bit further upstream now, right? A little different place, okay? And you drop the rock. And you count off the seconds, you say, according to my calculation, we're several kilometers high. What's the delightful person say to you? You schmuck, I'm not going to go home with you. Okay? Just try, you don't have to do that. You don't have to, how could you do that? How could you impress that delightful person? There's a way to do it. Okay, we haven't talked about torques yet. But if you knew about torques, you could do it. Let me show you what to do. What you do, you don't drop the rock like that. You get your board. Long plank. Then you roll a great big piece of rock on it like that. That's counterbalance, all right? Then what you do is you crawl out on the edge of the board, okay? And you get out on the edge like that, okay? And you take your rock and you drop it. 1, 2, 3, 4, 5. 5 times 5, 25. 25 times 5, 125. We're 125 meters high. What's the delightful person do over here? Delightful person says, oh, wow! Okay. Knocks the rock over, and guess what happens, huh? And so the rock comes down, here you go. You're in the water. You come up and say, fortunately, I can swim. What comes down back after you? You don't have to do it that way, gang. There's another way. Anyone know? Lee.
Throw the rock.
Throw the rock up in the air, right?
Throw it horizontally.
How about you throw it up in the air? Who's going to be lonesome? How about you take the rock and you throw it down, you start counting? Who's going to be lonesome, right? If you want to avoid lonesomeness, which way do you throw the rock, gang? Huh? You throw it straight out. Ain't that right? You throw it straight out. Now the time it takes to hit, it's going to be the same time to hit as if you dropped it. You see that? So it works out neat, doesn't it? I've done this before. I've been on cliffs. You want to know how high it is? Throw it straight out and count the seconds off. It's the same as if you dropped it. It works. It's nice. You know why it's nice? It begins with an F. It's physics. Good physics. Yay. Yeah. Would you like to see what a tough question would look like that has to do with everything we're talking about right now? How many say not particularly? Let me show you what a tough type question is that invokes all the ideas we've been talking about. Let me show you. A baseball pitcher at the top of a tower throws a rock. Throws a rock straight out. And it turns out the tower is 5 meters tall. And it turns out the rock, thrown as fast as the baseball pitcher can throw it, goes 25 meters downrange. Your question is this, and usually I'd give you a weekend to think about it. What is the speed of the ball to do such a thing? Think. Hint! We're throwing it sideways now. Hint! The speed of anything is the distance it goes divided by the time it takes. Without yelling out the answer, is there anyone that has an answer? 1, 2, 3, 4, 5, 6, 7, 8. Let's get 2 more. 9, 10. 10 people have an answer. 40 people have no answer. Not yet. Let's let the equation guide our thinking, gang. How fast is distance over time? The pitcher's throwing the ball horizontally. Are we given the horizontal distance that the ball goes? Yes, we are. And that distance is what? 25 meters. Huh? Are we given the time that the ball is in the air? No. Therefore, the problem can't be done. Boom! Impossible! Wait a minute. We're not given the time, but we be knowing enough physics to figure out what the time is. See how many of us can figure out how long is that ball in the air. Let me make it easy. Let's suppose the dude just took the ball and dropped it. How long would it be in the air? Begin with a W. 1. But now he ain't dropping it. He's throwing it sideways. Check the person sitting next to you and see if the person sitting next to you is any resource in this problem. How many say it's 1 second? Show of hands. That's right, it's 1 second, gang. Because if it's going to take 1 second for something to fall 5 meters, and if you toss it out, it's still 5 meters vertical. It's like this thing over here. If this is five units down, this one comes out, it's still 5 units down, stretched out, huh? So it's going to take 1 second. So 25 meters divided by 1 second gives you 25 meters per second. Isn't that neat? There's some good physics there, gang. You like? Let me ask you a question. Would the ball be in the air for a longer time if there were a hill like this? Yes. Would the ball be in the air for a longer time if the Earth's curvature came into play? Yeah, it turns out if he throws that thing really fast, it might go so far out that the curve of the Earth is falling away. You see that? In fact, if he keeps throwing faster and faster and faster, he might throw it off the Earth altogether. Isaac Newton, physics typed, in 1700s, figured it out like this. Consider a mountain on the Earth. It's so high that it's up above air drag, and put a cannon up there. Now we're up above the drag of the air. If you fired a cannonball and there was no gravity, none, the cannonball would go in a straight line. But the cannonball doesn't go in a straight line. You know why? Because there is gravity. And gravity pulls it down. So what the cannonball does, it maybe falls like that. You know what would happen if I fired it faster? Be up for a longer time. It would still fall, wouldn't it? Let's suppose I fire it even faster. Longer to hit, or same time to hit, or less time to hit? Longer to hit. You know what I'm going to do now, gang? I'm going to put all the powder in. All the powder. I'm going to fire that thing really fast. Watch this. Is the cannonball falling? Is it still falling? So you got to move the cannon out of the way. Isaac Newton realized that if you fired a cannonball fast enough, it would fall all the way around the world. Around and around and around. That speed is high. Very, very high. But that's how we put things into orbit. We simply put, instead of using a cannon, we put things on a rocket and piggyback it up and get up there, and then when we get up here, we fire it out, and something falls around and around. Next time you see the space shuttle on TV, see the people inside and you see the views of the Earth, realize that space shuttle is falling around and around the Earth. It's going so fast sideways. By the time it falls a little bit, the Earth is curved the same. Isaac Newton was able to calculate how fast the cannonball would have to go. Isaac Newton was a genius. Do you know there are people on this campus that can calculate how fast the cannonball would have to go? And you know what? There are people in this room who could calculate with no pencil, no paper, only their minds, how fast the cannonball would have to go. And I think that 80% of the people in this room can make that calculation if I guide your thinking. Can we try it? You want to see who you are? Let's try. Let me give you a geometrical fact. We live in a world that's curved. We know it's curved because if you put a laser 1 meter off the ground and you fired a laser beam out over the desert, like the Mojave Desert in California, perfectly flat for miles and miles and miles, if you fire that laser beam, you'd find out the laser beam over here looks like people it's pointing up. But it's not pointing up yet. It's just that the Earth is curving under. Let me give you a fact that a geography teacher can tell you about. If you go out 8 kilometers, that's 8,000 meters this way, you'll find out there's a 5-meter vertical drop. You will be 5 meters higher than you were over here. We live in a world that for every 8 kilometers you go out, tangent-wise, there's a 5-meter drop. That's all I'm saying. But that 5 meters turns out to be interesting, because we've learned something about 5 meters, gang, haven't we? What have we learned about 5 meters? Let's suppose we take this laser, throw it away, and we put a cannon, Newton's cannon. We put it right here. and we fire a cannonball. Is that cannonball going to follow that straight path? Answer begin with an N. HC. How come? Because it's not beginning with a G. Don't understand it very well, but we have a little bit together. What is it called? Gravity. Gravity going to pull it which way? Up or down? Down. Watch. Let's suppose I fired the cannonball at 2 kilometers per second. That means it'll go 2 kilometers in a time of 1 second. So after 1 second, it's going to be out this way. How far out that way? 2 kilometers. Okay? 2 kilometers is going to be about here. But it's not going to really be there, gang. It's going to be underneath there. How many people will be knowing how far underneath if there's nothing in the way? Begin with an F and with an I. Try it. 5 meters. It's going to fall 5 meters. I don't care how fast you go this way. It's going to fall 5 meters underneath. Ain't that true? All right. So it's really going to be like, well, like this. It's really going to be right here. And if it's still going to be airbound, I would have to dig a trench or something like that. Gang, this is not to scale. Yeah? It's not to scale. So it turns out my cannonball will follow a curve. That's hardly going to put me in orbit. I'm going to hit sand. So I fire it faster. I fire at 4 kilometers per second. 4. If I fire at 4 kilometers per second, how far out would it be in 1 second? You see it's 4 kilometers? But it ain't really going to be up there. Where's it going to be? Underneath. How far underneath in that 1 second? How far? See if you're sitting next to someone who knows. In that 1 second, how far underneath? Is it still 5 meters? Yes. It's still 5 meters. Let's look at that. But you know what? The sand's in the way, so you got to dig. Take a shovel, dig it out. The path would really be like that. In a little while, I'm going to walk over here. I'm going to put my arm right up here. And I'm going to ask the question, how many people in this room have calculated how fast a satellite got to go to orbit the Earth? I'm going to ask that question, but not yet. Let's suppose I fire this thing 6 kilometers per second. 6. That means in 1 second, how far downrange?
6 kilometers.
6 kilometers. That's pretty far in 1 second. That's going to be way out to here. Is it really going to be up there?
No.
No. It's going to be where? Underneath. How many people be knowing how far underneath? More important, how many people say, I don't know. I mean, at 6 kilometers per second, I don't know that one. Come on. How far underneath, gang? 5 meters. Okay, so it's really going to be like this. So I got to dig. I got to dig a hole. I got to get a shovel again. Now I got to dig. Notice I don't have to dig so deep. Now the path it takes is like this. Let's suppose I fire it at 7.5 kilometers per second. It's fractions. Can you do fractions? 7 and 1/2 per second. How far downrange at the end of 1 second? 7.5. That's about here, right? You're really going to be up there? It's going to be underneath. How far underneath? Still got to dig. I wonder maybe there's some speed I could fire whereby I don't be needing a shovel anymore. How many people in this room can calculate in their head how fast a satellite has to go to stay in close Earth orbit? How many have made that calculation that Newton made in your head right now? Can I have a show of hands? 8 kilometers per second, right? You're holding a book and the kid walks by and says, hey, I see you be getting a college physics book there. Say, I'll be taking college physics, honey. The kid say, maybe you can be answering me a question. I always wondered how come the satellites don't fall down? How come they don't? You're a college person, tell me. You say, well, it's all in the math, kid. It's all in the math. The kids say, what's all in the math? Let's suppose the kid wants to know. Could you tell the kid why the satellite's stand over? You could say to the kid something like this, hey kid, hand me that rock. I'm going to drop it, tell me what you see. Kid says, you dropped a rock, it fell straight down. Kid, I'm going to do it again, tell me what you see. Kid says, this time you dropped a rock, but it was moving when you dropped it. So it didn't drop straight down, it curved over. Yay. Kid, I'm going to do it again, tell me what you see. The Kid says, ah, you dropped it again, but this time when you dropped it, it was going even faster, so it made a bigger curve and fell way down there. You say, right on, kid. Now, kid, I got a question to ask you. What if I move my hand so fast that the curve it makes matches the curve of the whole world? Then where will it drop? And the kid, boom, he's got it, he's got it, he's got it. He sees it. He says, it'll never drop, it'll keep falling around, it'll never hit the ground. That's all there is to it? And you say, begin with a Y. Yes. He says, ain't it really more complicated than that? No. It's that simple. Think about these ideas. See you next time.
Oh.